weren't very biased. Okay? And that's where we invented the LASLs, these linker amplified shotgun libraries. That was mostly David Mead at Lucigen that did that work. And basically there you shear your DNA, you add primers, and you amplify it. Okay? And if you do that correctly, you can get very quantitative things. They match what you put in. Okay? And then when the 454 came out, we just needed a lot more DNA than we could get using that method, and we actually went to the 529 amplification, so the multiple strand displacement stuff. And that has all this bias, right? So we're going to probably go back to this. Okay, so everything since about 2006 to now has been 529 for the most part in our lab. Okay. All right, the other things that are coming up, it used to be that people used affinity columns for grabbing viruses out of seawater. Not so good. Then there were these different filtering methods. The one that we always used were tangential flow filters. And now there are these precipitation protocols. There's a couple of them out there that we might consider for grabbing viruses out of the ocean. That we haven't decided. The question is we're moving around a lot of water, so we don't know the easiest way to do this yet. If we want to take 100 liters at each site or something, right? How do we do that? Okay. So this is still an open question. And the best one of those so far, I think, is the Sullivan's one, which is the iron chloride one, which is the one that is what they use on the Terra Ocean stuff. And then the other thing that's going to happen, okay, if we get the LASLs correct, that will be really nice. However, there's a workaround for this stuff, and that's actually these recruitment plots. Okay? And these are coming out, so what we're going to start seeing, so Maxify and FACS depend on having very representative samples. There's ways that you can actually do it. The math is almost exactly the same, and we're getting so much sequence nowadays that you can actually get pretty long contigs, right, out of a sample de novo, and then you can throw your fragments across that, right, and you can just ask, what coverage did I find in that sample, and you should be able to recruit or make exactly the same calculations as you do here, okay, with just the recruitment plots, which will be a nice addition to at least to the statistical analyses. And then finally, the other things that we need to start considering. So, cesium gradients versus filtering and DNA scene alone, right? So we've used this more in the human system because there's often not enough viruses to work with. So this is Alander, is that how you say his name? Do you remember? Alan? It's something like this. I think he's the guy that did most of this early work, where he just uses DNA, buttload of DNAs, to like get rid of as much free DNA as possible, and just filtering to do his work. And he's been doing that for a long time. John Mokilian and Yan Wei actually did some of that for the human samples. In the gut samples, we probably have enough, we know from the cesiums enough about what the virions are nowadays, so we may be able to just sequence the whole thing and pick out the viruses from that, and that's mostly because of LANCE. And we might consider not always doing cesiums, right? So that's going to be a tricky one. It's not going to work in like CF log, right? Because we'll never, or right now it's not going to work. But in some of the other systems, we may be able to get away with not doing that, doing this part. So consider this, and this just came out this year, and I think I sent it around to the labs, where they're starting to look at where they put, and they've looked at all these things and what the recovery rates are and so forth, and thinking about how you might modify these things to make them more quantitative as well as qualitative. All right, so in the end, this is what I want you to take home, is that basically we know that viruses are, and in particular phage, are moving genes around around the globe probably, in ecologically and evolutionary relevant timescales. So it seems like they're moving things. We know almost nothing about this part of it, actually. Okay. We have pretty good evidence for here. Not much, of course, in what's going up in the atmosphere, right? We assume that that's happening out there, but we don't know much about it. Yes?
Do they not have any viral stuff from the deep sea drilling program?
A little, but no. That's
So looking
been
at
mostly
bacteria.
Matthias Middlebow and who's working with Matthias?
I know USC has a big
Hiking.
center for this
Yeah.
now.
There are some things that are going on, but not a ton
Okay.
there. Yeah, and there is a drop off as you go into Dan Navarro's group showed that as you go deeper into the sediment, you go from your 10-to-1 to more like a 1-to-1 virus to bacteria ratio.
Oh, because they're passive moving, they can't move as well?
Who knows? Really, we don't know why. It may be that activity is slowing down or something, but there's definitely something going on there. That's also true in the deep sea. It goes from about 10-to-1 more to a 1-to-1 as you move through that.
I have a question.
Yes.
Have you done anything on looking at age and year?
No, we did some bad stuff at one point.
Was that Jesse?
No, that was Maya and Ulali and Aki Hawkstrom had done some of that. Mostly because Aki wanted to go flying around in his plane, but
Yeah, not so much catching.
But I haven't seen much come out. Anybody else seen any literature?
Osaka did that whole
What?
steam thing.
The steam thing, but that one's a little funky because we don't know how to think about that one. But yes, he did do some of that, so Rick did some.
Yeah.
Anything else?
Weren't you collaborating with the Don guy up at Irvine?
Yeah, so we should take, so that would be, so the guy that's doing, for the CF project, he's doing the trace gases, but he actually has this large atmospheric chemistry project where they're going up high and they're getting big things and they know how to sample correctly. So that would be the place to look, quite honestly. But no, we only talked about it, we never did it, yeah. Mark and I also built a sampler that would go up in a
Weather balloon?
weather balloon, yeah. But we never actually flung it out. But now we could just get someone to jump out, right?
Yeah.
We could get GoPro and Red Bull. No, just close it now.
So, Jeremy the first jump, Stephen the second jump.
I like that. I think we need
We'll
Ben
jump into
post-cesium
the
chloride
boiling
first jump.
No.
Yeah. And we'll put a little bucket of water for them to land in.
So the thing is that, you know how it's like dinoflagellates and all this stuff in the air. You probably find like a lot of very similar viruses in the ocean.
Yeah, I mean, they're going to be there.
Yeah.
And they should be moving really rapidly. I mean, the places that they pop out, and where we do know something is pre-metagenomics and pre-direct counts and everything, there was actually a lot of sea spray work where people were looking at the viruses hopping. They basically hopped out in the sea spray. So you can see that part. And I'm sure that there's a ton of literature about buildings and crap,
Yeah, I
like
was
how
gonna
the
say,
viruses
buildings,
move
air
and all that stuff.
conditioning,
Yeah.
yes.
Yeah.
There's all that
Industrial.
work with the sands from the Sahara, right? And blowing
Yeah.
across Japan and all that.
Yeah,
we don't
yeah,
talk
and,
about
and particularly into the Alps. That's actually probably the most famous one because in the Alps you can actually cut
Right,
through and you
right.
can see Sahara sand, no Sahara sand,
Yeah.
and there's a ton of microbes, and they seem to not have much microbes when they leave the Sahara, and they have a lot when they
Right.
are in the collect in the Alps. So it seems like there's something going on in the atmosphere. Yeah, but I actually haven't kept up with aerobiology much at all. We did some when we did the with the Singapore group, Eugene, Rune, and those guys. We actually did the HEPA filters out of the vents of a building, like 2006, let's say, and we did look at the viruses a little bit in that sample, so there were actually tons of viruses caught in those filters, but we never really figured out are they phage or the human viruses or anything past that. Yeah. And there's ecology of the built environment is a Sloan Foundation initiative right now, so hopefully someone will figure a lot of that out for us. Okay. And then, just to give you this final thing, so if you've never looked at this, this is actually a figure that I think is important, okay? Because it kind of summarizes where we probably still are. In the world out there, you basically have this viral metagenome, let's call it, but phage is the main thing that we're concerned about. And it's organized within the viruses as modules. Okay? And modules are the equivalent of operons. We call them modules in phage. They're actually called operons in bacteria. Okay? And what that means is that they basically start with the same promoter and as read through by the same polymerase. Okay? All right, and these things are very, very closely tied to, of course, our prophages, because that's what they are, our plasmids and our genomic islands. And for various annoying reasons, people call these like pathogenicity islands and evolution, or what do they call them? Echo islands or some other. But this is basically these groups that are about 50 kb, which is suspicious, right? 50 kb